today I want to present regarding the topic on structural analysis of temporary soundproof walls. And then the presentation in this part of this phase, in the introduction, in the second numerical approach, and then so the net research, and the final I make some conclusion with the previous result. 20분 정도 하고 있어요. Temporary soundproof wall are temporary structures in the form of the barrier installed for purpose of minimizing damage from noise and dust around the construction site and protecting the living environment. In this study, the foundation of the temporary soundproof wall is manufactured in the form of the screw pipe and the press fitted through rotation to form a foundation for the ground, thereby reducing the noise and the construction environment waste and developing an eco-friendly construction techniques to minimize carbon dioxide emissions. First, as a manufacturing method of prototype or produced based on the drawing, and then dynamic load simulation was performed on the temporary soundproof wall based on the screw file. After 3D modeling was performed for structure with the dimensions of this kind of size, 3 by 3 mirror and 6 by 2.5 size. And when pressure conditions were applied to analyze the factors of the structure. And also, we did in this phase, and the simulation was performed by applying two types of facing method, namely the integral type and the back-forth method, is the result of structural analysis. In the case of 3 by 3, maximum displacement of the bolted type increased by 4 millimeters compared to the integrated type, but the maximum stress was almost the same. And on the other hand, in case of 6 by 6 type, the maximum displacement of the bolt type increased by the 30 millimeter, and the maximum stress increased by about 40 megapascal compared to the integral type, but it was structurally stable at the 82% of the yield strength is about 275 megapascal of the HB. This is kind of we did in this is first before I did some kind of study, you have to understand the H type and the base plate and the ring and the label plate. So this kind of this is a screw type of, okay. And then this like we did some higher from the ground like this, and then there's some this is kind of wall, soundproof wall in there, so we can do like this kind of. So we're using the HB, and then this is kind of we did some kind of size we apply. And also there are some wind velocity like this, and then we apply this is outer conditions of the atmosphere conditions. We have to, so wind velocity we apply the 28 meter per second, and the topographic conditions are like 1.1, and the topographic coefficient 1, and the important factors is 0.745. Wind pressure coefficient, the shaft is 1.2. Gust influence factor 1.9. Air density 12.25. To simulate this kind of conditions, we have to make some computational grid. So like this. Okay. There is some unstructured grid we applied in this way. Previously, we thought one kind of the parts. So we applied to calculate so we applied all kind of grid edges according to this node. Okay. So in these cases, we applied the unsymmetric unstructured grid applied in these cases. This kind of the reinforced plate, and this is base plate. This is an important part for this. And also another one is this is fire. Okay, so this fire and but you look at this. There is some screw in there. Okay. And also we have to understand to analyze this kind of thing. For the structures of the material, we use the material characteristics like this as SS275. This is the kind of steel. The modulus of elasticity is 210, and the yield strength is 275, and the Poisson ratio is 0.28. Tensile strength is 400. Density is 7,500. And then also for the fire cases, we use this kind of steel, which is called the SDP 550. And there is some one. And then for pin pipe, using this kind of thing. There's the SDP 275 steel, and also we use the PVC cases. So this is kind of before we analyze, we apply the numerical scheme. We have to understand the material characteristics, so we have to write that in this way. This figure shows some kind of result. Look at this. Let's see. There's some. This is the integral type structure. This is 3 by 3. So that we can see there is some displacement and the stress distribution diagram. Look at this. This is lower low number. This is a higher number. This is much more strength in there. Okay. They're like this. And this is ground, and this is fire. Twist it and fire it, and this one. Okay. Let's some more description of this. Okay. structure analysis were formed when the wind pressure acting on the condenser direction to the soundproof wall was 703.5 Newton per meter square. The height of soundproof wall was 3 meters. The high beam spacing was 3 meters. The upper and the lower part were integrated. As the result of that displacement distribution and the stress distribution were shown in this phase. Okay. Structural analysis was applied when the wind pressure acting on the condenser direction to the sunroof wall was about 335.5 Newton per meter square. The height of the sunroof wall was about 3 meters. The high beam spacing was 3 meters. The upper and the lower put were bolted, and the distribution and the stress distribution were shown in figure 8. Let's say more figures. This is one, and this is kind of figure 8. We see there is some difference. This is 6 by 25 mirrors. So there are size differences. Which one? Previous one is size is 3.5. This is 3 by 3 cases. Okay. This is 6 by 2.5 meters. There's the size of differences, so we can see there is much more differences over there. And finally, let's some more dots in there. This is kind of 3 by 3 display for this displacement, the stress distribution of the bolted structure. Okay. This is 3 by 3 cases. And then this is the displacement stress, and then distribution of the bolted structure 6 by 2.5 meters. So there is much more differences like this. Let me description a little more according to this. Okay. Let's see. Okay. Structural analysis were performed when the wind pressure acting on the soundproof wall in the normal direction was 735.54 Newton square meter. The height of soundproof wall was 6 meters. High beam spacing was 2.5 meters. The upper and the lower parts were integrated. As a result, the corresponding displacement and the stress distribution diagram were shown in the figure 0.9. Structural analysis were performed when the wind pressure acting on the soundproof wall in the normal direction was 735.54 Newton meter square. The height of the soundproof wall was 6 meters. The high beam spacing was 2.5. Similarly, the upper and the lower parts were bolted. As a result, the displacement distribution and the stress distribution were shown in figure 10. This one is figure 10. Okay. This one is figure, I guess this is figure 10. Let me summarize from the previous research. Summarize some kind of I have to show some kind of comparison study of the previous research. The table shows some kind of thing. Is a 3 by structure, 3 by 3 meter cases. Integrated type is maximum displacement 6.39. Maximum stress 98.19, and the stress ratio to yield stress is 35.7%. On the other hand, bolted type for the case, the maximum displacement 10.81, maximum stress 98.20 megapascal. Stress ratio to yield stress is 35.7, which is same as the previous one. And then for the structure, 6 by 22.5 meter structure cases, integrated type, maximum displacement 88.39 millimeter. For the bolted type cases, displacement is much more. 180.65 millimeter. But integral type for the maximum stress cases 88.59 megapascal. But bolted type cases 226.69 megapascal. For the integral type stress ratio to yield stress is 68.6%. Bolted type for the stress ratio to yield strength is 82.4. This is kind of summary of the previous research. Let's make some conclusions of previous research. 거의 됐죠? 20분? In this case, the CAE analysis was performed on the structure to understand the structure, stability of the self or supporting HE, sound layer, barrier, structure of Jimbang ENC company. CAE analysis was performed and analysis by applied screw type 5 structure and soundproof wall dimensions 3 by 3 and 6 by 2.5 meter. Let's make some conclusion. The wind pressure applied to the sound barrier were calculated at 735.54 Newton per meter scale were evenly distributed in the normal direction. In addition, in order to understand with the existing bolted structure, to case of bolted facet and the method and the one-piece method were applied and the structural analysis were performed for each structure for comparative analysis. In this case of the 3x3 structure, maximum deformation of the H-beam increased by about 0.4 millimeter compared to the integral type. In the case of the 6x2.5 structure, maximum displacement H-beam increased by about 30.1 millimeter during the bolting compared to the integral. In case of a 3x3 structure, there is no difference in the maximum stress of H-beam of integral type and bolt type. The yield strength is about 36%, so it is considered to be structurally very stable. In the case of the 6x2.5 structure, maximum stress of H-beam increased by about 38 megapascal. Finally, we compare to the 3x3 structure, which explains the strength of the 6x2.5 structure increased by, and due to the uniformly distributed wind pressure acting on the sound barrier, which is thought to be due to the load applied to the bolted part of the base plate. This one.